and welcome to day 30 of daily Leetcode challenges. Let's begin our daily challenge. Question 567, permutations in string. Medium level question, given two strings S1 and S2, return true if S1 contains a permutation of S1, or false otherwise. In other words, return true if one of S1's permutations is a substring of S2. Okay, so let's see. First of all, the definition of a permutation, basically any order of characters inside of S2. Any reordering of characters inside of S2. I'm guessing that this means that S1's permutations have to be a contiguous subarray of S2, which means that, let's see, one solution right away could just be to generate all different permutations of S1 and then basically make a window, a traveling window in S2 and see if that substring, which is actually just the traveling window of S2, is in the collection of permutations of S1. Let's see some examples. S1 is AB, S2 is EI, DBA, OOO. Output true. Why? Because let's see. This is not a permutation. This is not a permutation, but BA is a permutation of S1, and OOO obviously is not. We don't matter. So output is true. How about another example? Example 2, S1 is AB, and S2 as, oh, it seems very similar, EI, DB, O. Okay, and the A is just one off from where it was here, but that already does not make it a substring or a permutation because there's an O separating them. Okay, let's look at the word constraints, if there's any word constraints. So there's S1's length is greater than 1, but S2's length is less than 10 to the 4th. So there's no constraints that that could make this. For example, I'm thinking that if there was a top constraint on S1's length, a max constraint on S1's length, then maybe we could get away with just generating all different permutations of S1 and then going through the window of S2 and just making sure, well, seeing if that window is one of the permutations. But since there's no limit on how long S1 could be, there's another approach to this where basically we encapsulate the idea of looking if a window is in some permutation of S1 using a hashable structure. What that really means is as the window is traveling, as the window is traveling in S2, we're going to be hashing that window, and hashing that window would mean that, what we're first going to do is we're going to hash S1 or some data structure that contains S1, and then we're going to be hashing the window of S2 continuously as we're progressing through S2, and we're going to see if those two hashes are the same. The reason why that works for us is because a hash of two objects that are the same will also be the same. And so if we are hashing a structure that is, for example, ordered, then the output should, of those two, okay, so basically, look, hash s1, and then we're going to select a window. Oh, no. We're going to, first we're going to create a data structure from S1. We're going to sort that data structure and hash that data structure. Then we're going to select a window of S2. We're going to sort, select a window of S2, create that DS2 essentially, then sort that DS2 and hash that DS2, and then just a simple compare between these two hashed data structures, and if they're the same, then we know that the permutation exists in S2. Okay, now for the sorting part. So this sorting could be a little bit tedious and could probably add to our time complexity. So another method that we could take is, since we know the different types of characters that there are, we could just make a list of length 26 that contains all zeros. And we probably don't even have to hash, we can just compare if those two lists are the same. Let's call this array 1, which is just of length 26, and then we'll have another array 2 of also length 26, all with zeros. Now we're going to basically, this is, let me do this. Let me keep this thing here so we can see what we're doing. So this is us creating that common data structure. We're not going to sort because our data structure doesn't need sorting. It's always, we know that, for example, A is going to be in the first index and Z is going to be in the last. And we actually don't need to hash, I guess, because we can just straight up compare these two arrays. Now we have to populate R1 and R2. Let's say for I in range len S1, we can say R, and then pick out the place where this is. Order, by the way, of a character gives us the ASCII index of that character, so we're going to say order of S1 I minus order of A. This is because minus order of A is because there are 26 letters in the English alphabet, and we want A, which is the first one, to be at 0, index 0, and we're just going to say the same thing for R2, S2. Let's see what this looks like now. R1. We see that R1 now looks like a, so this is essentially just going to be our hash. We don't actually have to hash it because we can compare arrays, but AB is exactly what we expected. A has one occurrence and B has one occurrence. Cool, and same goes for the R2. Now, we're going to say for I in range len S1, len S2, we're going to first append to S1 the new character. So R2 ord S2I minus ord A plus equals 1, and then we need to subtract, but what we need to subtract is the character that just got out of range of the window, so that's going to be 1 minus len s1, and this is going to be minus 1. And now we're going to compare. We're going to see if r1 equals r2, return true. And the last, false. Okay, and what else? What else do we need? We need this. We need to say that for the first instance where we just populated R1 and R2, if, sorry. Okay, sweet. So, okay, yeah. So what is happening in a few short words? We've chosen our data structure to be an array of length 26, representing all the characters in the English language. The value of each index is going to represent the number of occurrences of that letter in the word that we've currently looked at. The word that we're calculating all the permutations of is S1, and we're calculating its quote unquote hash in this simple for loop. And as we're doing that, we also are building our first window of S2 array. And that window is also of length S1, because ultimately a permutation needs to have all the, or the same number of characters at least as S1. And so we are doing that in one simple for loop. And right away we're checking if the hashed window is the same as our original hashed S1. If so, return true. If not, we have this additional for loop where we basically shift that window one step to the right. We add the new character that is next encapsulated by the window and subtract the character that just got out of the window. Check if the two hashes are equal. If they are, return true, else return false. And that should be it. We submit. And obviously, of course, as usual, we have issues. What? Runtime error, string index out of range. S1 is AB while S2 is A. So this can't be, oh, I see. What's happening is S1, okay, so basically if len S1 is greater than len of S2, return false. It can't be that S1 is greater than S2 because then no permutations of S1 can be in S2. So, awesome. Okay, and yeah, it seems like we're beating a good amount of people. Beats 80, almost 90% of all the solutions. And I mean, we're all up there, so I'm guessing that all of these solutions are pretty similar, and yeah. I guess this question is really testing hash, like how you know how to use hashes, because the other more naive solution is obviously to build up all the different permutations of S1, which could be done, but is tedious. Anyway, thanks for watching. Bye.